Okay, let's continue. So last time we started from a absolute convergent power series. With radius of convergence. Yeah, okay. With radius of convergence R. Then we know this function is infinitely differentiable, and the kth derivative is equal to n from k to infinity, n minus 1, n minus k plus 1, a n z minus a to power n minus k. So we know this the power series the derivative can be written as this power series with radius of convergence R, radius convergence R. Okay, so same radius convergence, and also we know that when we have those derivatives, the coefficient a sub n is represented as 1 over n factorial the nth derivative evaluated at a. You have to evaluate at the center. Okay, so this is what we know. And from this long computation, well, this theorem is very, very important, and the proof is very technical. And the typical is very typical. So it's very important for you to recall every step of the proof and know why we have those steps, the reason behind each steps. Okay. Okay. So from here, we know that the differentiable function is also continuous, and this one is infinitely differentiable, so it is continuously differentiable, right? So corollary, if the series sigma n from 0 to infinity a sub n z minus a to nth power has radius of convergence r greater than 0, then f of z as a function is analytic in this open disk centered at A with radius R. Right? Okay, so this is the first large class of analytic functions. No, second. First class large analytic functions is rational functions, right? We know that with addition, multiplication, quotient, we can get all the rational functions analytic in its domain. And here we get all the power series analytic in the convergent disk. Right? Okay, so if we have this corollary in our mind, then the exponential function, remember that exponential function, it is series n from 0 to infinity z to n over n factorial. This one, it has radius of convergence infinity, so it is analytic It is analytic in the complex plane, right? Because the radius of convergence is infinity. We had examined it by using R is the limit an absolute value of an over an plus 1. Remember that. Okay. Next, let's examine a well-known fact. If G is open and connected, G is open and connected, and f from G to C is differentiable. With f prime of Z is equal to 0 for all Z in G, for all Z in G, then f is constant. Okay, so if you have a constant zero derivative, then function is a constant. Well, this is a well-known fact in the calculus. Why we have to prove this again in the complex analysis? Well, how did we prove this theorem in the calculus? In the calculus, in order to prove this, we need the mean value theorem. Right? We need the mean value theorem. Fb minus Fa over b minus a is equal to f prime of c something. And because f prime of c is equal to 0, so fb is always equal to ma. Fb is always equal to fa. So that's the reason behind the theorem in the real calculus. But this only works for the real line. We have such real line property. So in the complex differentiability, in the complex differentiation theorem, there's no corresponding mean value theorem so far. So it's not automatic. This theorem is not automatic. Okay? So now let's see how do we prove it. Okay, so we are going to show it is a constant. So we fix Z0 in G. We fix Z0 in G. And let W0 be the value of function at Z0. Okay, we have one value. We're going to show f is always constant at this W0. So put or define A to be the subset of G such that f of Z is equal to W. F of Z is equal to W. Okay. And then we have to show, we need to show that A is equal to G. A is equal to G. Well, this part we're going to use this extra condition, connected. Remember, we always assume G to be open because we're going to discuss the differentiability of function f. So G is always open, it's natural. But in this proposition, we also additionally add G to be connected. That is used here. That is used to prove A is equal to G. G is connected. G is connected if and only if, this is from the point set topology, G is connected if and only if G is equal to the union of A and B with open connected. G is union of A and B with A, B open and A intersect B empty. With this condition, G is a union of two open sets, disjoint union, and AB intersection of A and B open. This implies either G is equal to A or G is equal to B. Okay, G has to be one of them. In other words, G cannot be G cannot be written as a disjoint union of two non-empty open set. G cannot be the union, disjoint union of two non-empty open sets. Cannot be. If it written like this, then one of them must be the empty set. Okay, so this is a open connected. Okay, so here we're going to use this connectedness to prove A is equal to G. So we will show that A is open and closed. Why A is open and closed? How do we get closed? Because if B is open, then its counterpart, the complement, will be closed, right? This is a equivalent condition about A union B, A be open, and A intersect B empty. A be disjoint union, okay? Disjoint union. This word is misleading. Disjoint union means those two open sets have no intersection. Yeah, it's not disjoint union. Disjoint union has different meaning. Two non-empty disjoint. Yeah, this is better. Not disjoint union. There's another. This represent different stuff. Okay, we will show that A is open and closed, and A is not empty because A contains at least one point Z0. And this implies A must be G. So if A is not open empty, then B will be empty. Okay, so that's the meaning. So here we use the topology. And let me see. It's 48. Let me try to. Connectedness, yeah, 14, page 14. Okay, so this concept is on page 14. Connectedness is discussed on page 14 in the textbook. So if you are not familiar with this, you go back to the page 14 and review it. Okay. Okay, so let's see what we have. We're going to show it is open and closed. How do we show A is closed? How do we show A is closed? A is closed if and only if A contains all the limited points. Okay, so let Z be in G and let Zn be a sequence in A with the limit of Zn is equal to Z. So we have a limit point. And f is differentiable. This implies f is continuous, for sure. And f of Zn, in A, f of Zn will be W0. So f of Z will be the limit, f of Zn will be the limit of constant W0 will be W0. This implies Z is in A, right? So this is natural. A is a natural closed set. A is a natural closed set. So this closeness is checked. Closeness is checked, right? Okay, so now we are going to present A is a open set. So A is open. A is open though. Let A be in set A. A be in set A. So, well, set A is a subset of G. G is open, then there is an epsilon greater than 0 such that the ball centered at A with radius epsilon is totally contained in G. So we have A, we have open disk centered in G. This is G. Okay. Well, we're going to pick up whatever point inside this open disk. Let Z be in the open disk, be a epsilon, be a epsilon. This is Z. Then you just use straight segment to connect the A and the Z. Okay. Let G of T be f of T of Z plus 1 minus T times A. This is straight segment, and then you evaluate f along this straight segment. That's a G of T. And here T is between 0 and 1. T is between 0. All right. Well, this is a real variable, but complex value. Complex value, f is complex value, but T is a real variable. Real variable, complex valued function. So let's check what is the derivative of this G. The derivative of G is well, let's see. We can write it in a fancy way. You see, we will see why it is important in a fancy way. So it's a T minus S times Z plus S minus T times A. And this is T minus S times Z plus S minus T times A over T minus S. Why we write this simple quotient in such fancy way? It's just because you see G of T, G of S. What is G of T or G of S? Let's write it in a clear way. So it's a Tz plus 1 minus Ta minus Sz plus 1 minus Sa and over T minus S of z plus s minus t of a. And this. So basically, we just try the chain rule. So this is actually the external function. The inside is internal function. This is a chain rule. And this denominator is actually the difference between tz plus 1 minus ta and sz plus 1 minus sa. That's a difference. So if we compute the limit, let t approach let t approaches s, we will have the limit t approaches s gt minus gs over t minus s is equal to f prime. You will let t be s, but you differentiate f. Right? And then this part is z minus a. Z minus a. But, well, you cancel that, you will get a z minus a. But this one, f prime is constantly 0. So this is always 0. Okay? This is always 0. Remember that we get the derivative g. This is g prime of s. G prime of s is constant 0. And g is complex valued real variable function. Complex valued, actually just two-dimensional. You see, when you have a complex value, you can consider it g of a t as a g1 t plus I times g2 of t. And the g prime will be g1 prime of t plus I g2 prime of t. So if g prime is 0, it actually implies g1 prime, g prime of t is 0. If and only if g1 prime of t equal g2 prime of t are both equal to 0. And then you can apply the mean value theorem for g1 and g2 and vt. You will get if this one is 0, it implies g1 of a t, g2 of t are both constants. So mean value theorem, the important thing is that the input should be a real numbers. Originally, we say we don't have mean value theorem because that's not a real variable. It's a complex variable. It's not a straight line. Okay? So here we have straight line because input is a real variable. Even though the output is complex variable, but you just complex variable, two-dimensional, you just have more component functions. That's not the problem. Okay, so after we got g prime of s is equal to 0, for s between 0 and 1 implies this two-dimensional function. G is constant, a constant function. G is a constant function. G is a constant function. F of z is g of 1, which is equal to g of 0, which is equal to f of a, is equal to w0. And remember, what is z? Z is, where is z? Z is here. Z is arbitrary point inside the open disk. Hence, this open ball centered at A with radius epsilon will be a subset of A. So A is open. A becomes open. Okay? A is open, A is closed, A is not empty, then A is equal to G. Open, closed, non-empty, then A is equal to G. A is equal to G, everything's done. Right? So this proof This proof is very, very topological. This proof is very, very topological. First of all, you have to understand what what connectedness is. What connectedness is. So connectedness, if and only if it cannot be written as a union of two non-empty disjoint open sets. And second, you have to understand the mean value theorem. Mean value theorem, we don't have mean value theorem for the complex variable function, but we do have mean value theorem for the multi-dimensional real variable functions. As long as the input is a real variable, it doesn't matter how many components we have. You always have the mean value theorem for each component, and then join them together, you will have constant function, right? So that's how. Well, this is the end of the proof. Very nice. So the constant derivative implies the constant function. Zero derivative implies constant function. Zero derivative implies constant function. All right. Now let's back to the study of exponential function. Let's call it f of z, which is n from 0 to infinity, z to n over n factorial. If we do differentiation once, right, we will have this. But remember that when n is 0, the first term disappears. So you will start from n equal to 1. Now factorial n cancelled. The first term disappears before you cancel anything. You cannot cancel 0 from 0, right? 0 factorial is 1, but in the numerator part, 0 is 0. And then if you reorganize the indices, so you have the same thing. So we see what? We see the derivative of exponential function is itself. The derivative of the exponential function is itself. So here, be careful. When n is equal to 0, the first term disappears. The first term vanishes. So you don't consider the first term. You change it from 0 to 1. All right. And okay, so we have the derivative of e to z is e to z itself. That's the first thing. Let's see the first thing. And second, let g of z to be e to z times e to a minus z for arbitrary complex number a. Then we can have the derivative. Remember, all the derivative formulas are the same, the sum, difference, product, quotient, because they are more or less the arithmetic. So you differentiate first one and copy the second one, plus you copy the first one, you differentiate the second one, you have to apply the chain rule, right? You have to apply the chain rule. So the derivative of a minus z is 1, and this will give you 0. G prime of z equal to 0. G prime of z is equal to 0 for all z in C. This implies G prime. So G prime of z is a G of z is a constant. G of z is a constant W. For all z in C. All right, now let's apply it. E to 0, we know that e to 0, we're back to the initial power series. E to 0, z is equal to 0, only first term survives. E to 0 is 1. So far, this is the first evaluation of a power series we have. E to 0 is equal to 1. So g of 0 is equal to e to 0 times e to a minus 0 is a. E to 0 is 1, so it's e to a. So this constant number is e to a. So we get g of z is constantly e to a, and g of z is also e to z times e to a minus z. Hence, we have our formula. This is our second formula, the product rule. The product rule. This is equivalent to, these two things are equivalent. The e to a times e to b is equal to e to a plus b. But remember, this is not like the one term times the other term, like e squared times e to 3. It's not in that sense. Remember, originally we believe this is e times e times e times e times e, so that's e to 5. That's the power idea, how we understand the power function. But here we define e to z as a power series. You can try to put you can try to put z equal to 2 and do the product. That's not a simple job. So we have to use calculus to get this general formula, because we defined in a different way. Okay, so this is our original understanding. It is based on the definition of power series. This is from our new system. Okay, and from this one, you just let a be 0. If you let a be 0, we get what? A is equal to 0. E to 0 is 1. We get this. So e to z times e to negative z is equal to 1. E to z times e to negative z is equal to 1. So this implies e to z is never equal to 0 for all z in C. Okay? So exponential function is never equal to the 0. And also e to negative z is 1 over e to z. The negative power means you flip it. The negative power means you're going to flip it. Right? Okay? It's 1, 2, 3. This is a 3. This is a 4. Let's see another one. Exponential function. We will summarize them, but let's label them one by one. Exponential function is sigma n from 0 to infinity, z to nth power over n factorial. If we put complex conjugate, it's complex conjugation of z to nth power n factorial. Complex conjugation just changes the sign of a imaginary part, and it is commutative with a power function. So and the denominator is a real number, so you can just have something like this. And the complex conjugation is commutative with a sigma, so it doesn't matter you have infinite sigma or the finite sigma. Infinite sigma, you just get a limit. Okay, and this is e to z bar. Okay, so when you have the complex conjugation of z, it's actually just put the complex conjugation to the exponential function. All right. Okay, so well, let's see. From here, this is one of the important stuff. If we have e to I theta, theta is real. For real theta, e to I theta is a pure imaginary number. Then its complex conjugate is going to be e to negative I theta. All right, and this one is equal to e to I theta times e to I theta bar. So it's a e to I theta opposite value square. Right? E to I theta opposite value square. This is the property like this. So z bar is equal to opposite value of z square. The complex number property. On the other hand, if you apply the additivity, e to I theta plus negative I theta is e to 0. E to 0 is a 1. E to 0 is a 1. So what we have? We have them. ei theta. This is a real number. Square is a 1. So ei theta opposite value is equal to 1. You put square or you don't put square. Doesn't matter. Okay? You have that. This is 6. Let's just review everything we have just from this derivative and the constant function. And now we have a general complex function, complex variable. Then complex variable is a real z plus I imaginary part of z, right? Then we have e to z bar, e to z bar. E to z bar, it is equal to e to z whole thing bar. So this is the opposite value of e to z square. Opposite value of e to z square. Whatever complex number you multiply it by its conjugate, it's a modulus squared. Okay? And the other hand, this is e to real z plus I imaginary z. This is real z complex conjugate minus I imaginary part of z. And you add them, you have additivity. So the plus minus canceled. It's a e to twice of a real z. E to twice of real z. Right? So what we get they equal to each other. Twice, remember that twice is real part of a z times real part of z squared. Right? Square. So here squared, so we get e to z modulus is e to real part of z. E to z modulus is e to real part of z. All right? Okay. Here we have a very small thing. We didn't mention it. Well, this is a 7. We naturally take the square root to get e to real part of z. Why don't we put a negative sign? Why this is always a positive number? The thing is the following. If you have a positive number, then e to x is power series based on the definition. Of course, it's positive, right? Power series, it's always positive. And if we have negative number, remember negative number is the reciprocal of 1 over e to x. Now this time is still positive. So if you have a real input, the exponential of a real power is always a positive number. So that's why here we can directly remove the square and get the equation. All right, so what we have, let's summarize what we have. We have, okay, I'm going to do it one by one, list. First, the derivative is itself. Second, we have product Here a be a complex numbers, not real number. Sorry. Number 3, e to z is never 0 for all z in C. Number 4, e to negative z is 1 over e to z. Number 5, where's number 5? Number 5 is here. E to z bar is e to z, the whole quantity bar. It's compatible with complex conjugation. Number 6, ei theta is equal to 1. Number 7, e to z modulus is equal to e to the real part of z. Well, let's put the number 8. E to real part of a z is always positive. E to x is always positive. It's always positive. Okay, so that's the property we more or less get from this simple computation. And you will realize that all these stuffs are the properties of real exponential functions. So they are exactly properties of real exponential function. Sorry. So that's the reason we name this power series by the natural exponential function with a complex input. And remember that in the real world, we have this. Let me write it in the complete way. Exponential function has a Taylor series like this, Maclaurin series, and we have a cosine of x as let's just pick up even part, 1 minus x squared over, and plus x to 4 factorial, and minus, and sine of x is x minus x cubed over 3 factorial plus x to 5 over 5 factorial minus, it's plus minus alternating. So because of this analog, we define the complex cosine and sine. So just simply replace x by z. So cosine of z is going to be 1 minus z squared over 2 factorial plus z to 4 over 4 factorial and minus, actually, and dot dot dot, and we keep this coefficient here, negative 1 to nth power z to 2n over 2n factorial, and dot dot dot. If n is odd, if n is odd, it is negative. If n is even, it's positive. It's a sine. Cosine, that's cosine. Sine is z minus z cubed over 3 factorial plus z to 5 over 5 factorial and plus negative 1 to n z to 2n plus 1 and 2n plus 1 factorial. Okay, so that's how complex cosine and sine, complex trigonometric functions by the same power series. And you can examine that each of them will have the infinite radius of convergence. And in this case, you cannot use r equal to the limit an over an plus 1. Remember that an is a coefficient of n's z to n. Here there's no z, so there's no a1. A1 is 0. There's no z cubed, a3 is 0. So there are infinitely an which are not which are 0, so you cannot put the denominator. So this fails. You cannot use. I say you cannot use. You have to use the definition. A similar thing happens for the sine. Okay, and if you examine the relation between sine and cosine together with the exponential, you will see that the cosine of z is e to iz plus e to negative iz over 2. And the sine of z is e to iz minus e to negative iz over 2i. Okay? All right, so just manipulate with this iz. Remember, this z is a complex number. This iz is not a pure imaginary. It's another complex number. You rotate it 90 degrees. And with this property, you do a square, you will get cosine of z squared plus sine of z squared is still equal to 1. Is still equal to 1. And e to iz is cosine z plus I sine of z. Cosine z plus I sine of z. So these two conditions are also kept in the complex variable. You know them in the real variable. This is also correct in the complex variable. Okay, if we have we'll stop quickly. If we have z equal to I theta, theta is real, pure imaginary, then we will get I theta is cosine of theta plus I sine of theta, ei theta. And in this textbook, they gave it another name called cis theta. Cis theta just means cosine theta plus I sine theta. It is ei theta. Okay? And if you have a complex number z is its modulus rei theta. Rei theta, right? Rei theta. And then you have exponential of the let's also use x plus iy. E to z is e to x plus iy is e to x. This is a modulus. Remember that it's modulus e to iy. And this part is a real part, so it's a exponential of the real part of z times what? Times e to iy, imaginary part. Y is an imaginary part. So let me write this. Times ei imaginary part of z. Imaginary part, this is exactly the theta. So imaginary part of z is the argument of e to z. Argument. ei theta, this is argument of e to z. Argument of e to z. Okay? Okay, so that's let's stop this discussion here, and we will continue in the next video. This lecture is not done. Okay, thank you.